So, welcome to last week of our problem solving session. So, we will be covering or basically briefly discussing the topics of week 8. Along with that, I'll try to give my solutions for week 7 assignment as well. Okay. So, those of you who have joined today for the first time, I am Oshandra Paul, and I am a PhD scholar at IIT Kanpur in the Department of Chemical Engineering, and I'm working in the field of tissue engineering, where I have gained small, very recent experience, okay, very recent experience in working with biomaterials as well as using those biomaterial for applications like 3D bioprinting, electrospinning, etc. If you like to know more about my research, feel free to explore my website. The link is there on the screen. And if you have any queries related to the course, feel free to drop your query in the discussion forum. And if you are joining here, and you can directly ask me as well. So, like this, we have been doing our sessions every Saturday from 4 to 6 p.m. And here's the joining link. So this will be the last week of that, and all the recordings and the notes, they are all made available to you by the NPTEL people. So feel free to revise through them afterwards. So again, those of you who are joining for the first time, you won't be having your chat option available to you. So you would have to use your mic to speak, or you can also raise your hand and ask your query. So whichever way seems good to you. But you have to speak in order to raise your query. So like briefly, one of the topics discussed in this week is what are bioceramics. So in previous week we saw about polymers, and before that we saw metals. This is the last very important class of biomaterial, that is ceramics. So ceramics, you all know, they are materials of very high strength. Remember the stress versus strain graph. So they are of very high strength materials. And the primary bonds that are present in ceramics, they are of ionic nature, as well as you will get some covalent bonds in them. So in polymers, most of the bonds are covalent, whereas in metals, there are metallic atoms. So in this way, in the by categorizing what type of bond they have, you can categorize them. They're polycrystalline compounds. So if any one of you is familiar with TEM or transmission electron microscope, through this technique, you can actually see the crystallinity in your sample. So yeah, so it is having a very nice unit arrangement of unit cells, and in a very ordered manner that gives the property of polycrystallinity. There are various types of ceramics in the nature. There are, sorry, so there are silicates, metal oxides, carbides, hydrides, sulfides. So these are all ceramics, and they can contain both metallic compound as well as non-metallic compounds like alumina or magnesium oxide, silica. So these have a metal component like aluminium, magnesium, silicon. Silicon is not exactly metal, but basically a non-metallic thing, and oxygen, which is a not of metallic property, right? It is an electronegative atom. So in this way, they are very much different from the classes of biomaterial that we saw previously. There are various ionic salts like NaCl, the salt, table salt that we eat, then zinc sulfide. So these are also having ionic bonds in them, just like the ceramics that we talked about, like alumina, magnesium oxide, and all. But they are not biomaterials. Please take a note, they are not biomaterials. Okay, so not all ionic bond containing materials are biomaterials, but the ceramic or the bioceramics, they are having ionic salt-like properties. So this is a point to keep in mind when you're trying to define ceramics or bioceramics. Then there are various advantages to using these type of biomaterials. There are very high compressive strength. Then they show a very good wear and corrosion resistance. So it is that is why they are heavily used in orthopedic applications, because whatever implants that people are using, they will in the body undergo some kind of wearing and tearing motion. Okay, so they will degrade over time. So if we coat it with some ceramic, bioceramic material, then it will provide that resistance to it. Then they can be highly polished. Okay, so for an application, hello, am I audible? Okay. Mm, am I audible? Okay, great. Sorry. So I was just checking my connection because the place where I am, it often gets poor connectivity. So as I was saying that it can be highly polished, it can be made highly polished. So it becomes an advantage for various kind of application which requires a polished surfaces for that particular purpose. Then there are various bioceramics which are inert, or as well as inert means they will not respond, or they will not show any biological response, or the cells will not adhere to the surface, and hence you won't see any biological response. Whereas bioactive is totally opposite, means it will show some kind of effect on the material, on the cells. So you can find bioceramics which are either inert in nature or they can be bioactive. So for applications where inertness is needed, you can use those ceramics. Whereas where you need some bioactivity to be observed because of your material, then you will use those kind of ceramics. So it gives a various this class of material gives a lot of options for you to explore. Then they have a very high modulus, like Young's modulus value is very high, but the tensile strength is quite low. It is not true for metals. If you remember, I think a few weeks back, 2 weeks back, I think we discussed about, or we compared the physical properties of metals, ceramics, and polymers. So, like, try to go back to my notes, maybe week 6 maybe. So there you will see very nice comparison I have shown in terms of various properties. So in that you will get a better understanding, or you can come, or you can better place this particular ceramic and where it lies in comparison to your metals and polymers. Okay, so in comparison to metals and polymers, it has a low tensile strength. That is what we mean by low. Okay, then fracture resistance is also low. Then only one problem is that it is difficult to fabricate. So using ceramics, the we as an engineer, or we as a biomedical engineer, find it difficult to uh, make complicated structures using only ceramics, which is why we have to use polymers. Polymers are much better options if you want to fabricate very complex architecture. Simple architectures we can with ceramics, but when we want some complexity, then ceramics, using only ceramics is not a good option. Polymers are much better. Even metals also provide ease, a very good opportunity to fabricate very nice structures. Okay. Now, as I was saying, that ceramics can be either bioactive again, they will show some biological response, and as well as they can be inert. Means if once it is put inside the body, it will not show any biological response. It is inert, right? And there are other class of bioceramics that is biodegradable. So, for whatever application you are going to use this type of ceramic, they will show, they will like decompose inside the body or degrade inside the body for a long period of time. So, if your application demands that kind of specification, then you can go for this type of ceramics. So names I have highlighted here. So inert, if we see the inert bioceramics, we have alumina, zirconium oxide, carbons, sintered HA means hydroxyapatite. Then if we want to use ceramics which are bioactive in nature, say HA. So there are various studies people have done using HA, where they incorporated HA within polymers and saw that it promoted osteogenic properties like osseointegration, uh, and then osteoconductivity. Means basically helping the bone cells to mature and mineralize, okay, secrete more and more mineral components and ultimately regenerate the bone. So in that application, we can say that HA has bioactivity in it. Okay. Then there are various biodegradable ceramics also, like calcium sulfate, then coral, the calcium carbonate from corals, that is biodegradable. Then there are various calcium phosphates which are biodegradable. So HA is also a type of calcium phosphate, but the number of carbon phosphate groups, etc., they all vary. But there are other type of calcium phosphates which are biodegradable. So there is alpha TCP. TCP stands for tricalcium phosphate. Then there is OCP, octacalcium phosphate, DCPD, dicalcium phosphate dihydrate. So these kind of calcium phosphates show biodegradability. So where these kind of biodegradable materials can be used, you can use it to make something for that is going to go inside your body, say for bone tissue engineering application, where you want some bioactivity. Okay, you want to trigger the bone cells to show some maybe differentiation or proliferation. But you at the same time you also want that particular tissue engineered construct to degrade inside the body. Then rather than using HA, you can use a simpler derivative of calcium phosphate, just like tricalcium phosphate. And I think it will again show the bioactivity. So these kind of simple ideas, they are like it's like very well explored. People think of it, and whatever they find, they publish it. So I'm definitely sure this kind of ideas are already published. But that is an example how people are finding applications for these type of materials. Now, if so I took this particular table from a research paper where they were showing the examples of various bioceramics and where they are currently used. So mainly the areas of orthopedic surgery, then dental applications. These are the two main areas where bioceramics are heavily used. If we see for orthopedic applications, you will see that various implants are coated with some ceramics, like porous ceramics, like alumina, HA coatings. Why? To create a interface, okay, between the implant and your biological tissue. To create that interface, they are provided this kind of a coating. Or they want to do some bone replacement, means some part of your bone is broken and through a biomaterial you are trying to replace that. And in those cases it is favorable that you put something inside the body that supports regeneration. Okay, you cannot you cannot really make, so no one in the world has yet any biomaterial that is exactly like your bone, to be very honest. Okay, we are all trying to mimic our body's complex architecture. So at the end of the day we want to create something that helps the body. That is the research goal of all the biomedical engineers, to create the body, to create something that helps the body to regenerate itself. So they are making some implants that allows gradually the body's own bone cells to proliferate and mineralize and create a new bone new bone. That volume of the new bone should be sufficient to replace the lost bone. So for these kind of applications, these materials like HA, tricalcium, phosphate, etc., are explored. Then for tissue engineering or in dental applications as well, people have used alumina, then HA, like for making dental implants. Bioactive glass is also used. Then for tissue engineering application, that is to coat any substrate so that particular type of cells only grow. There also people have used alumina and HA. So these are some briefing about a very big class of bioceramics. Uh, for those of you who have already watched the lectures, it might be a nice summary for you. For those of you who haven't, maybe it's a good time to go back and watch the lectures. Okay. So, acha, any queries so far? Um, was I was I able to make you understand everything? Yes, no. Are you there? Anyone? Okay, so you have understood. Maybe you can unmute and speak. Any queries from your side? I hope I was not very
No,
boring
ma'am.
to you.
No, ma'am.
No queries? All right, great. So I will assume that rest of you also have no queries. So I'll move on to briefly discuss another important topic. So as an engineer, you have made your implant. Okay. The next step is to process it so that it can be used in human. So what all processing or steps will you do? First step that you should do is sterilization. Okay, this is a very, very, very important. Like I cannot stress how important it is. You whatever thing you put inside your body, that has to be sterilized. What do you mean by sterilized? Sterilized means it should be free of all free of all microbes. Okay, free of all, if possible. Ideal case is 100% free of microbes. But in realistic thing, like based on the technologies that we have, we cannot really reach up to 100%. Okay, but we have some standards set that helps us understand whether this level of sterilization is sufficient. Now, why we want any implant to be free of microbes? Because if it enters inside your body and you don't know what that microbe is, so it can disturb your homeostatic condition of a particular tissue and cause various kind of infection, and that infection can be very serious. Okay, so we don't want that kind of conditions to arise. That is why we have to sterilize anything that goes inside our body. Mouth, what you eat doesn't have to be sterilized. Okay, our mouth is a house of microbes. What uh, I'm talking about, those implants or those things which you put it by mechanically cutting into your tissues, your skin barrier, okay, and then putting it. I'm talking about those kind of implants. Even the equipments that they use for surgery in hospitals, the bed sheets, their gowns, their hands, their like everything, they are sterilized to their best level. Okay, even the entire operation theater has mechanisms to entirely sterilize the room because the person is going to be cut open, right? So sterilization is a very, very, very important step. Uh, so what are the methods for sterilization that people use? One method is steam sterilization. So in our labs, like we run cell culture labs, there also for growing cells, we maintain sterile conditions. So we use autoclaving. It is a way of sterilizing under using steam. Basically, we use steam, but the steam is at high pressure, okay, and at a very high temperature as well. So this is actually steam sterilization. Now there are various types of autoclaving, short cycle, long cycle autoclaving. The standard one that we do is we use one 15 psi, 15 psi pressure and a temperature of 121 degrees Celsius. Okay, to sterilize everything that comes in contact with our cells. So that is one method, steam sterilization, also called autoclaving. Then another method is using radiation. So again, this is a very, very frequently used method that we use in our lab setting. For as what radiation do we use? We use UVC. That is of around 295 nanometer. Okay, UVC is around 295 nanometer. Now this particular this is a short wavelength radiation, and the energy is not too high, but it is enough. It is enough to kill the bacterial, fungal, any kind of not. It will not kill the viruses, but most common contamination that comes is bacterial one. So it can kill the bacterial cells or bacterial spores. So this type of radiation, UVC radiation, that is why is also called germicidal radiation. Okay, germicidal radiation. During COVID period, people started selling various kind of equipments that had this UVC light, and under the UVC light, people started sterilizing their mobile phones, their papers, okay, their phones, tablets, laptops, so that any germs that come in contact through maybe hand or something like that doesn't get propagated to others as well. So this method of sterilization is again very, very heavily used everywhere. The least used method of sterilization is ETO, ethylene oxide gas. It is like a very, very toxic gas, and it is very flammable. So in lab settings, we don't use it. At least I have not known any lab who uses ethylene oxide to sterilize their environment. But in industry, I think they use. Also, other than I forgot to mention in radiation part, people also use gamma radiation. So UVC radiation is of low energy, whereas gamma radiation is of high energy radiation. And this also have been used to sterilize various plastic wares. Suppose those plastic wares which we use for culturing cells and all. So radiation and steam sterilization are the most common ones, whereas ETO is not favorable in lab settings. I don't know, maybe in hospitals they use it, but just for your information, there are three methods. All right. So I hope the content for this week also it was quite light. So now I'll start with some numericals, which will help you to solve this week's problem, this week's assignment problems. So before I started, if you have any queries on anything that I discussed so far, any queries?
No.
Yes. So you said no. Okay, okay. I thought you are going to have a query. So I think Murali Krishna, he has responded. He has no queries. So anyone else? Any queries from anyone? So many people who are joining today. You guys, I have seen your names at least, not your faces, joining for the last 8 weeks. So I think you should be more comfortable by now to interact. Don't feel shy. You can ask even silly question. Don't worry.
No queries, ma'am.
No queries. Okay. So now I'll move on to few numericals. The first numerical is already on your screen. So the question says that there is a stainless steel rod whose dia is 15 mm. So let me write it down. Dia 15 mm. So radius will be 7.5 mm, right? And it is coated with HA, hydroxyapatite. So it's a raw stainless steel rod and it is coated with hydroxyapatite. So part A, what we have to do, we have to first find the thickness of this coating so that the Young's modulus of the composite is 209 gigapascal. Okay. So how should we start? We will use the mixture rule to help us out. Okay, uh, we'll frame a equation actually, and to frame that equation, we will use the mixture rule. So if we apply the mixture rule, which we have already done in last week's problems, what was that? It was the Young's modulus of the composite is given by E1 V1 plus E2 V2. Now, this was in terms of volume fraction. Okay, V1 and V2 were the volume fractions of the respective components. Like if one component is stainless steel, other component is HM. But here, for this question, we don't have any data that will help us to calculate the volume. Only we have the radius or the dia. We don't have the length. Okay, so which is why for this question we cannot use this expression. We have to frame slightly different expression. So we will use E is equals to E1 A1 plus E2 A2, where A1 is the area fraction of say stainless steel, A2 is the area fraction of hydroxyapatite. All right. So we have to find the area fractions. After we do that, we have this E1 value, E2 value, and E value. Okay. And this area fractions will have a variable. What is that variable? Variable is the coating thickness. So let me just write here. Let the thickness be X. Okay, let the thickness of coating be X. So if we look at the area of only stainless steel rod, it's a cylinder, it's a rod. If we do a cross section, it's a circle. So basically, we have to use the area of a circle, which is pi r squared. So in our case, it is pi 7.5 squared. The units don't change. Okay, we are going to work in the unit of mm only. They have asked the answer in mm. So that is why 7.5 mm is the radius. We will use as it is. Then the area of HA plus stainless steel, then what will happen? Um, or a better question would be, so let me remove this line. we should ask what is the area of HA coating. That is the better question. Means your this is a circular cross section of the rod, and the coating is outside. So inside is your stainless steel SS, outside is your HA. So inside area we have outside area, that is the coating of the HA coating we have to find. So what it will be? It will be 5. Now 7.5. If the radius is 7.5, this one, and X is our thickness of our coating. The total radius of the rod with the HA coating will be 7.5 plus X whole square. Okay. Minus the area of the stainless steel cross section, that is pi 7.5 square. Makes sense? I hope it does. So we now have the area of stainless steel and area covered by the HA. Now we can find A1 and A2, that is the area fractions of each of the components. How we do that? A1, that is for the stainless steel. It is pi 7.5 square by pi. So we can actually simplify this expression a bit, this expression, so that it becomes easier. Take pi outside, 7.5 plus x whole square minus 7.5 whole square. Now use the algebraic equation a square minus b square. It is what? A minus b, a plus b. We can use that here to evaluate. So 7.5 plus x minus 7.5 into 7.5 plus x plus 7.5. Does it make sense so far? What it will come out to be? Anyone? Solve this expression yourself and let me know. Have you done it? Solve this simple algebraic equation and let me know what will be the area of HA coating.
X into X plus 15 into 5.
Again, can you repeat? Let me just quickly write it down. X into
X plus 15.
X plus 15 into 5.
5.
Okay. So I'll let me check. Is it correct? Yes. Yeah, it's correct. So this is the expression for the HA coating. Now remember, we have to find the value of X. That is the answer that they are looking for. So we have to first find the area fraction values. So SA1 was the area fraction for stainless steel. So the area for stainless steel will come in the numerator, and the denominator will be the sum of the both areas. This is one expression. Area fraction of HA is pi x into x plus 15 divided by pi 7.5 squared plus pi x into x plus 15. Okay, so these are the area fractions you have obtained. Now we have to put these area fractions in this expression. So E, it was what? It was, I think, 209. Wait a second. The value won't be 209. So let me rectify it quickly. I think it should be 2010. Yeah, the original question it was 2010. Yes, just it was a minor typing error, so it will be 2010. So E is 2010 gigapascal. E1, what is E1? That is Young's modulus of stainless steel. It is 200, right? It is 200. Then what is E2? E2 is 300 gigapascal, right? So we have the values. What will be the final expression? It will be 2010 equals to E1, that is 200, into A1, that is pi 7.5 square divided by this sum that we have in the denominator plus E2 is 300 gigapascal into pi x into x plus 15 is again divided by this sum. Now, we have to simplify this expression. The expression that we got here, we have to write it in a simplified manner so that we will get the expression in terms of x. Okay. So all of you quickly use your arithmetic knowledge to give me an expression for x. Let me do it, okay, on my own on a different piece of paper, not on the screen, because I want you guys to do it. Because if I write it on the screen, you will just copy paste. I know people how they are learning these days. So yeah, do it. Solve this particular expression and give me a simplified expression using x. It's very basic, you know. You guys have must have done it in your maybe class 9, 10th level. So it's very basic. So what's the expression? Did anyone solve it? Okay, so if you haven't, it's actually very easy. I will not tell you how to do it because you should be able to do this on your own, but just to save time, let me write what I have found. So if you solve this particular expression, you will get 9x squared plus 135x minus 56.25. This is the quadratic equation, all right? And you will get two values of x. You will get two values of x. Now, how to find those two values of x? Again, recall your +2 level mathematics. For quadratic equations, the solution or the value of x is given by something like this, if you remember, minus, so this expression in the form of ax squared plus bx minus c. This is the form of this expression. So this type of expressions are solved using the values of x for this type of expressions are obtained using this particular equation, minus b plus minus root over b square minus 4ac divided by 2a, where for our case the values of a is 9, b is 135, and c is minus 56.25. You just have to put these values of a, b, c, and you will get the value of x. Please do it. While you do it, I just have to pick a call, right? Um, just, sorry. So find the value of x now. Put the values of a, b, c. So put the values of a, b, c in this particular expression and tell me what you are getting for the value of x. Got it? So what will be the value of x? Solve this expression. See, I'm also doing. If anyone gets the answer before than me, feel free to help me out a bit so that I don't have to do the entire thing.
Ma'am, is the value of x minus 15.4?
X, so you will get two values of x. What are the two values?
0.40 and minus 15.4.
Okay, you are getting 0.40. Another is minus
Minus 15.4.
15.4. So these are the two values. Now tell me, for this particular expression, can you get a negative value? Or is the coating thickness should be of a negative value? No, right?
No.
Coating cannot be having a negative thickness. So then your answer will be this. X will be equals to 0.40 mm. Okay, so only one guy was doing it. Others, I don't know what you were doing it. So I think this is the correct answer. Yeah, this is the correct answer. Okay, now moving on to part B. Uh, we are given the densities of this stainless steel and hydroxyapatite. We have to find what will be the average density. So we have to use mixture rule now for finding density. Using mixture rule, density of the overall composite will be equals to individual density of component 1 into area fraction. So instead of volume fraction, we are just simply substituting with area fraction plus rho 2 A1. So this is for SS, this is for HN. Now we've obtained the value of X, which is 0.4 mm, correct? So and we have the expressions for area fractions, right? What was that? For A1, we had pi. So just remove the pi's, then we'll have 7.5 square divided by 1.5 square plus X is 0.4, then 0.4 into 15.4. If you find this value, we'll get the value of A1. You guys start doing it. Then for HA, the area fraction will be 0.4 into 15.4 by 7.5 square plus this 0.4 into 15.4. Now, use a calculator to give me the values of A1 and A2. Anyone? So, did anyone do it?
A1 is 0.9.
0.9, okay. A2?
0.10.
0.10. Basically 0.1 and 0.9. Okay. So Then we have obtained the value of A1 and A2. Then what will be the value of rho? Just we are given rho 1, rho 2. So what was rho 1? Rho 1 was 7.9 and rho 2 was 4. 7.9 gram per cc, rho 2 was 4 gram per cc. Fit this value into this expression. What we'll get? 4 into 0.1. Just quickly use a calculator and let me know the value.
7.51.
7.51. Acha, 7.51. Can you tell me again the value of A1 that you got? What is the value of A1 you got?
0.9012. 0.90.
0.9012 means 0.9. Okay, 0.9. And it is 0.1. Okay. Then it will work. 7.5, 7.151 is equal. So this is the answer that we are getting. I think this is the correct answer. So yeah, this is the correct answer. So I hope those of you who are doing with me, you have understood the logic behind this question and how to approach a similar question. Now we'll move on to the next question. So the next question is saying that people have tested 1 billion implants. They were tested for sterility. And what they found that 1100 of those implants were contaminated. Now, does this qualify this sterility assurance level, or in short, SAL level? So the options are yes, no, cannot judge, and sometimes it will. So from the lectures, what do you understand by SAL? Anyone?
Your voice is breaking.
Actually, I was asking, is my voice better? Hello, is my voice better?
Internet is poor on your side, I think.
Okay. So let me just check my internet connection.
No, ma'am, you're audible.
I'm audible? Okay, I'm audible. So hello, I'm audible now. I have actually fixed my internet connection now. So I must be audible.
Yeah.
Hello? Yeah? Okay. So as I was asking, if any one of you have gone through the lecture on sterilization part, so can you help us to understand what do you mean by sterility assurance level or SAL level? So people are actually basically it's a way of regulating. It's a way of regulating the implant and basically saying that this particular implant is suitable for transplantation. Other category which are not sterile are not suitable. So it's giving a benchmark or a line, straightforward line that beyond this level, beyond this line, the implants are not suitable for implantation. Okay. So this sterilization level says that SAL value should be 10. All right. If it is ideally, so it is the ideal case. If it is 10, then it means that there is a probability that in 1 million implants, only one viable or microorganism will be there. But accepted range of SAL values are -3, 10 to the power -3, 10 to the power -6. So if the number of the contaminated contaminating organisms, that is microbes, is fitting within this particular range, then only any regulatory authority will confirm or will allow you to use this particular implant for human application. Then only they will consider that your implant is sterile. If the level is increased, like greater than 10 to the power -6, then it will not get approval from this authority. It will not satisfy this sterility assurance level. So we have to find out the value of SAL first in order to answer this question. So how will we do that? So we are told that around 1,100 implants are contaminated. Out of how many? Out of 1 billion. That is 10 to the power -9. Now, if we simply take a ratio of it, what value are we getting? We are getting around 1.1 into 10 to the power -6. Now, this value is greater than 10 to the power minus. Even it is very close, only around 0.1 difference or 0.1 is more, but still this value does not fit into this ideal range, which is why the answer for this question is no. This particular implants or this batch of implants will not be considered sterile. They will be considered contaminated, and it cannot be used. This 1 billion implants cannot be used for human applications. Okay, have you understood what I'm trying to convey here? Okay. Moving on. So there's another question here. It's a very simple question actually. So the percentage of microorganisms remaining versus exposure time. So exposure time of autoclave sterilization, that is a type of steam sterilization, correct? Is this the percentage follows this particular relationship. The first case, let's say case 1, where we are using autoclave sterilization. There, the relationship between the percentage of microorganisms, let's say percentage microbes, is equals to 70 minus 2T. But T here is the time of exposure or exposure time. This is the relationship for autoclaving sterilization. Now, another case is there, the percentage of microorganisms remaining. This is live, actually, percentage of live microorganisms. After you have sterilized, some live organisms are still there on your implant. That is why I've written percentage live microorganisms, microbes. And for case 2, we are using the sterilization method, that is dry heat sterilization. Let's simplicity sake, I'm writing here dry heat or heat sterilization. Now, for that, what is the relationship? Percentage live microbes is equals to 80 minus 5T. And what is asked? We have to answer the question that at what time both the methods are equally efficient. What does this mean? It means if we were to compare the efficiency of these two techniques, okay, we are asked to compare the efficiency of these two techniques of sterilization. So, and that too, we have to find out how much time of autoclaving sterilization is like will kill the microorganisms, and that percentage of killed microorganism is same when we are using the heat sterilization. Okay, or in other words, I can say that how much time of heat sterilization is equivalent to how much time of autoclaving sterilization in terms of how many live microorganisms are present when both of these techniques are done individually on separate set of implants. Again, I'm repeating. We have to tell what time of autoclave sterilization is equivalent to time of heat sterilization, such that both the techniques will result in equal percentage of live microorganisms. Okay, so the key thing that we have to find is time. And how will we do that? We have to equate these two expressions. So equally efficient means, what is equally efficient? Again, I'm repeating. Equally efficient means percentage of live microorganisms with autoclaving is equivalent to percentage of live microorganisms with heat. So these are equal. When these are equal, that is equally efficient. All right. So we have the expressions, individual expressions. So let's equate it. 70 minus 2t is equals to 80 minus 58. So we have to solve for the variable t. So what it will come out to be? Tt is equals to 10. So t will be equals to around 3.3333. So around 3.3. So since we are not asked or we are not given any units for time, let's assume that it is some arbitrary unit of time, okay, or unitless time maybe, or it can be any time like 3.3 hours, 3.3 minutes, 3.3 seconds, okay. So, but the answer is 3.3. Understood the logic behind this question and how did we solve it? Okay, I'm getting only one thumbs up. That doesn't make me feel very good about my skills right now. Others, are you guys also listening? Are you also following what I'm trying to say? Yes? Okay. Moving on. This is a continuation of the previous question. So here what is given, you're asked after 6 minutes of sterilization, means in the previous case, there were two methods we saw, autoclaving and dry heat. So after 6 minutes of sterilization, with each of these methods on another two sets of implants, we have to find what is the percentage difference between the percentage of microorganisms remaining from both these methods. So we have to give the absolute number. So we are given the expression, right? For autoclaving, the expression that we had was live microorganism percentage is to 70 minus 2p. Okay. And heat sterilization, for heat sterilization, similar equation which was given to us was 80 minus 5t. Now t is given to us in this case. T is 6 minutes. So if we put the values of T in both the equations, what we'll get? Percentage of live microbes. So let's call it, this particular quantity as per P1. Okay, just to make things much more clearer, we are calling it P1. So P1 is equals to 70 minus 2 into 6 is 12, so around 58. So 58% of live microorganisms are remaining after autoclaving. And another case, let's call the percentage of my live microorganisms as P2. So P2 will P2 for heat sterilization is 80 minus 5. 50 minus 5 into 6 is 50. So after heat sterilization, only 50% of the microbes are remaining. So you have the individual percentages. You have to find what we are have to finally you have to find the difference. What is the difference? P1 minus P2. It is 8. This is your answer. And you are asked the absolute value. So 8 is your absolute value. Easy enough? Have you understood? Okay. So 8 is the answer. Now, if you have any queries in the middle, feel free to, ask me anytime. Don't hesitate. Don't keep your queries inside yourself. It will build up and it will create more confusion. So do ask questions. Now, another question that we have, the percentage live bacteria due to sterilization follows an exponential relationship. This relationship is, let me write it down, live percentage of live microbes or live bacteria here is equals to 30 into e to the power minus 0.01 T. Now here capital T is used, which is temperature. T is the temperature. So what should be the temperature to achieve less than 5% live bacteria? So first we'll have to find at what temperature should the sterilization process be continued or should be done so that 5% of live bacteria are present. And whatever value of temperature we'll get, uh, using that, we have to give a statement like what will be the value of temperature less to achieve less than 5%. So if we closely observe this expression, the nature of this expression, this is a exponential expression. Okay, means see e to the power minus some value. All right, or we can write 1 by e to the power some value. Let's a. Let's say a. Now this A here contains your temperature. So if we analyze how the temperature is related to the percentage of live bacteria, how these two quantities are related to each other. Okay, percentage of live bacteria. This relation is given by this expression, right? This exponential expression. Now understand this carefully. So if the temperature increases, okay, if the temperature is very high, what will happen to this exponential component? Will it increase or will it decrease? So let me write this exponential value like this. 1 by e, now e raised to the power 0.01 into t. Now, if this T value increases, if this T value increases, what will happen to the denominator of this fraction?
Increases.
Denominator part. Increases. Yes, increases. Denominator increases. Correct? So what will happen to the entire fraction then?
Decreases.
Yes, will decrease. So this exponential component overall decreases with increase in temperature. So that means what? More and more temperature we are increasing, this entire expression will decrease. And ultimately what we'll see? Percentage of live bacteria will decrease. Simple, right? जितना temperature बढ़ाओगे उतना bacteria मरेगा. All right? This is what this expression means to us. So first we have to find at what temperature only 5% of the bacteria are there. So whatever temperature value we'll get, we will then say that if we achieve, this is the benchmark basically, the temperature is our benchmark. So if we increase temperature higher than this benchmark, then we'll be able to achieve live bacteria percentage which is lesser than 5%. Got the logic? Again, I'm repeating. We first have to find the benchmark of temperature value. What is the value of temperature at which only 5% or exactly 5% of bacteria are there? And when we find that value, then only we'll be able to say that if we increase this temperature above this value, then will the live percentage or the percentage of live bacteria will decrease. It will be lesser than 5%. All right. Okay. I'm assuming that you have understood. If you have not understood, it will be clear, more clear actually, when I'll do the problem. So let's start. This is the expression given to us. So for 5% live bacteria, what is the value of T? So in this side, the left-hand side will be 5. It goes to 30 into e raised to the power minus 0.01 into T. So I have to find the value of T. For that, we can take, so we can take log actually, ln. First, let me simplify a bit. Then take ln both sides. Into T. Okay. Now what will be T then? T will be negative of ln 5 by 30 by 0.01. If you have a scientific calculator with you, you can then help me out with the value of T.
$179.
Yeah, but these chi matrices tell that it's couple chi matrix that you get from every.
Sorry, I didn't get your query. Can you repeat?
179. 179. Just telling the
179.
answer.
Okay, 179. Actually, I thought someone else was also speaking. So 179 you're getting. Anyone else getting anything different than this? Okay, so 179 degrees Celsius is the correct answer. So what does this value mean? This value mean if we achieve a temperature which is, if the temperature is greater than 179 degrees Celsius, then we'll be able to achieve percentage live bacteria less than 5%. Okay. So this is how you would, this is how the answer would look like for this type of a question. Okay. Go above 179, you will get lesser bacteria percentage. It means lesser than 5%. Okay. Have you all understood this question? Now, a very simple question. So from common sense, you tell me, you know what is contact angle, right? We have already seen what is contact angle and how it is related to hydrophobicity, hydrophilicity. Maybe for some of you, surface energy is a new term. But in a very simple words, if you would like to understand what is surface energy, it means how much that surface allows adhesion, okay, of any liquid substance. So means surface energy, the term has been used in various ways, like it has various definitions for different people of different areas. But when we come to contact angle and surface energy, then I think that is the best definition I can give you. What is surface energy? So now, if you have understood what is surface energy, means the energy of the surface that influences how the adhesion forces, like how well it will adhere to a particular liquid. Okay. Now you have to tell me how they're related to each other. Are they directly related to each other? Means higher the contact angle of a liquid, higher means you will get a higher contact angle for a surface with a higher surface energy. Okay. So again, let me direct relationship means contact angle will be higher. Let me write as CA for a higher surface energy, SE surface. Higher contact angle means if this is the surface, the bubble, the water bubble will look like this, like a almost completely spherical. Means the contact angle is higher. The contact angle theta is quite high. So this case is also saying that this surface will have a higher surface energy. This is first case. Second case is higher the contact angle, lesser will be surface energy. Now what this means? It means there is a surface like this and the water bubble is forming a shape, okay, that looks like this. Now if we look at the contact angle, is something like, it is going to be something like this, and the surface energy in this case is less. This contact angle is high basically, and exponential quadratic it doesn't really apply here, to be very honest. So I'll make things simpler for you and remove these two expressions or these two options altogether. Now you tell me, like based on what I've just said, what is surface energy, which of these relations, and based on the diagram that I have drawn for the water droplets, uh, guess, maybe a simple guess, which of these options are correct, A or B?
B.
B. Why did you guess B?
Surface energy decrease, at the same time contact angle is increased, so inversely to this.
Okay. So again, I won't say as of now what is, if she is correct or not. Others, what does your intuition says?
I have a doubt here whether the contact angle definition is in the counterclockwise direction or in the clockwise direction, the definition.
So let me show you an image like from my own work. So we do measurements of contact angle in two ways. So if you have ever used the goniometer, it gives you two values of contact angle. Uh, and people usually measure it in, I think, in clockwise direction. Yeah, clockwise
No,
direction. So,
no, not that way. From the professor's lectures, I remember it is the angle within the liquid drop and the tangent.
okay. I'll show you a real image of how the contact angle measurement is done. Okay.
Okay.
So maybe that will give you a better idea of how the contact angle looks like and how they measure it. So,
Means it will be like 180 minus the angle that you have showed on the slide here. The definition what I've seen from professor slides, 180 minus this one.
wait, wait. So this is let me just briefly stop sharing this slide. Okay. And share my own screen. So this is if you guys can see my screen, this is an image of a droplet on a substrate. The substrate is my sample basically, and here is the needle from which one drop has fallen, and the measurement, this 135 and 135.7, this measurement, the machine does it. So machine, you have to say that this is your surface, and with respect to surface, this is your contact angle. So within the droplet, they do it. Maybe my diagram representation was wrong. So this is the correct diagram of how the contact angle is measured. So we get two values of contact angle basically. And in our data, we usually report an average of that. So here is the report that the machine gives us. The contact angle, three values of contact angle between water and air at different interfaces, MRL. I'm not very sure what are these, but in the image form, it will become much more clear. Can you now get an idea? Maybe answer your own question now?
So this is basically the angle is measured within this one to the tangent within the
Yes,
liquid drop.
yes,
But
yes, yes.
whereas what you have shown is from the external, not from inside the
Yeah,
liquid drop.
that diagram is incorrect. This is the correct
Yes.
diagram. Okay.
Now, what is the correlation between the surface energy and contact angle? Can you explain?
Yes, yes. Actually, I was hoping you guys would guess because as I was, so let me stop sharing this now. Okay, so this representation is not correct in that case. Just forget about this one. So as I was saying, that surface energy basically tells you how well the surface has the tendency to allow adhesion of any drop. Okay, so the correct answer is actually B here. Why I'm saying, because if the surface has a much more stronger tendency to attract the molecules of the droplet, then automatically the drop will settle. It will not form a completely sphere. So the contact angle will decrease. Whereas if the surface is very having it will allow it will not allow adhesion properly. So adhesive forces, if they are strong on the surface, then the contact angle is lower. Otherwise, the adhesion forces is lower. The surface energy is high for the surface, so the contact angle. Sorry. I'm really I apologize, but as I was saying that the surface energy, if it is higher, then the adhesion forces are lower. Okay, then the contact angle. Okay, sorry. Let me write it down. So there is something called forces of adhesion, right? That directly influences the surface energy. They are directly related to each other. Higher the surface forces of adhesion, higher the surface energy. The surface energy is high, then the surface is more towards hydrophobic side. Its hydrophobicity increases. Phobicity increases. And we know from like previous lectures, the hydrophobic surfaces have a higher contact angle. So in theory, contact angle and surface energy, they are sorry. I think I have their hydrophilicity increases. Hydrophilic surfaces have a much more uh, stronger tendency of adhesion. So hydrophilicity increases. And we know that hydrophilic surfaces have allows lower contact angle of water droplet. Yeah, now this is correct. So as I was saying, if it is other way, if the forces of adhesion is lower, means that whatever functional groups that are there on the surface of a material, if it allows lower forces of adhesion between the water droplet and your surface, then the surface energy for the surface is low. All right. That means your hydrophilicity level will decrease and your contact angle for that particular surface will increase. Okay, I think I tried my best to explain. Murli Krishna, like, is it clear to you now?
Yes, yes, yes.
Okay.
So it's basically inverse relationship between them.
Yes, there is an inverse relationship between them. I was going to show this diagram. So this diagram actually says that the higher surface energy is there, the forces of adhesion is higher, means the water droplet finds it easier to adhere, right? Means the surface is more towards hydrophilic side, because of which the contact angle decreases. Alternatively, if the surface is such that it does not allow good adhesion, then surface energy is low in that case, and because of which is hydrophilicity basically decreases, and because of which contact angle increases. So briefly, so that was it from my side on the week 8 lectures. Okay, I will now quickly try to solve and give you my answers for week 7 assignment. Although I myself found that the answers for week question number 8 and question number 10 needs to be revised. So the other TA, Karthik, I contacted him regarding this. So if there is any correction from his side, he will definitely do it, but maybe he's not available right now. But I'll give you my answers anyway. Mm. So this is that slide I was going to show. So I've just simply written the answers for the first 7 questions. Um, So question 1 to 5, these are the answers, correct answers. I hope there should be no doubt in this. So you guys already know about alpha bonds and beta bonds, glycosidic bonds. So these 5 questions I think it is relatively easy. For question number 6, we had to use the mixture rule. Let me read the question number. Let me read this question from the assignment. So question number 6 was, you are given a polyester, which is a mixture of PET and PLGA, and the Young's modulus of each of these was 3.6 and 1.7. Okay, and you prepared a polymer blend of this PET and PLGA, which is 45% of this is PET, 55% of this mixture is PLGA, and then you had to use the mixture rule to calculate the Young's modulus. So for this, you have to find, you're directly given the volume fractions, right? 45% is 0.45, which is the volume fraction of PET, and 0.55 or 55% is the volume fraction for PLGA. Directly use this equation for mixture rule and you'll get the value. So I got the value of around 2.42, which is correct as per the assessment has been done. Then question number 7, here what we had to do, we had to find out the percentage load borne by PET or polyethylene terephthalate when the blend is subjected to a load. Now again, we have already done this. So we know load or stress is directly proportional to elastic modulus. So we have to use the definition of elastic modulus and the volume fraction to get this ratio. It is load borne by PET divided by load borne by total. Total means entire polymer blend. And I got the answer of around 61%. Okay. This again, as per them, it is correct. Then question number 8. So here it is written that after 10 days, 45% of PET and 30% of PLG has degraded. So what is the Young's modulus? So initially it was for PET, initially it was 45%, and PLG initially it was 55%. Now after 10 days, T is equals to 10. What we saw that PET, percentage of PET remaining after 45% has degraded is 45%. 1 minus 45 means 45 into 0.55. So if you do this, what you will get? This 45% have degraded, all right? And we have to find the remaining one.
Ma'am,
Yeah,
PLGA value is not 55%. In question 8, PLGA value is 30% in assignment question. But you
30%
write
has
55%.
degraded. Initially, it was 55%. No. Initially, 55% of the PLGA was there, and of it, 30% has degraded.
Oh, okay, ma'am. Okay.
Okay. That is okay. Let me- If we do this, so how much is remaining then? So 45% PET was there initially. Sorry, 45% PET was there initially. Of the 45% of PET initial, from it 45% have degraded. Okay, that is coming out to be 20.25% have degraded. So how much is remaining? 45 minus 20.25. We have 24.75% of PET with us. Similarly, for PLGA, initially it was 55%. Okay, and from it 30% have degraded. So if we like do it separately, we didn't do it separately for the PET part. So degraded, if you want to calculate degraded PLGA, 55% का 30% कितना होगा? Is around 16.5. So how much is remaining? Remaining will be 55. Huh? 38. What? How much?
38.5.
38.5. 38.5. Okay. So this much is remaining. But these are not your absolute volume fractions. Why I'm saying these are not? If you add it up, add these two up, you will not get a value of 1. Volume fractions, the V1 plus V2 should always add to 1. So we have to now find the volume fractions. Okay. So V1, that is for PET, what we are getting? 24.75 by 24.75 plus 38.5. You'll get a value of V1. Then what is the value of V2? That is for PLGA. It is 38.5 divided by 24.75 plus 38.5. So what are these values of V1 and V2? First is around 0.387, and for the other part it is 38.608. Now, do you think these are correct? How will you check it? You just add it up. I'm getting a value close to 1, I think. So we can actually modify it, but 6.1 कर दो, and this 4, 3, 8. Yes. So if we modify it bit, 0.39 हो सकता है ये. It can become 0.39. It can become 0.61. And if you add it up, you will get 100. So I'm using V1 as for the new blend, which is having 24.75% of PET and 38.5% of PLGA. So volume fraction, respective volume fractions are 0.39 and 0.61. Now using these volume fractions, you will have to calculate the Young's modulus, which is E is equals to E1. What was E1? E1 for, that is Young's modulus of PET is 3.3 into V1, 0.39, plus what is E2? E2 is the Young's modulus of PLGA, 1.7 into 0.61. Now do the calculation. Plus 7 to 0.61. I'm getting around 2.32. Oh, that's correct. That's actually correct and fits within the range that they are given. Okay.
Ma'am, can you turn to slide 17?
Okay. Here it is.
So ma'am, that PLGA actually get degraded to 30%, right? So in the PET also gets degraded to 45%. So
Yes,
in
yes.
PET case, you have subtracted that. I mean, like from 1 minus 0.4 for 0.45
Yes.
has done. So for PLGA, you don't need to do that. Like
No. I did the similar thing. I did same thing, just written it differently. Let me write it in another way. I did the same thing for PLG and PET. Okay, let me write it again. T is equals to 10, right? So let's do for PET first. PET, how much have degraded? 45% have degraded, right? Now, initially in the blend, there was 45% of PET. Out of 45%, so within that 45%, again 45% have degraded. Okay, so we have to take 45% of 45. This is the degraded one. Now, how much is remaining then? Whatever value you get, say A is your value. This is the degraded amount. Remaining is 45. This was the initial. This is your degraded amount. The initial minus degraded amount. You will get the remaining amount. This was 24.75. Got it? I did the same thing for PLG as well. See, if you write it in a bit simpler form, no, you can write it like this. You can take 45, okay, 1 minus 45. What you will get? This you can actually combine this expression. The 45 minus 45 into 0.45. So you're basically, so this value of A is this. I put the value of A here directly. Here, instead of writing A, I've written 45 minus 45 into 0.5 and taken 45 out and written in a simpler form. Same thing. Understood?
So, ma'am, for PLG, it will be like 55 into 1 minus.
55 into 1 minus 0.3.
Okay.
Do it. You will find the same value 24.75 and 38.5 for these place questions as well. They're just shortcut way. Don't go for shortcut if you don't understand the problem. First understand, then go for shortcut. I was bit smart myself that I did the shortcut way in the first one. Okay, I didn't intend to confuse you. The same thing I've done. All right. So this is the answer, 2.32. So if you just play with the values of V1 and V2, because you see there are so many decimal points here. So you might end up in the range, anywhere within the range, 2.2 to 2.35. Okay. Now, moving to question number 9. So question number 9 says that there is a natural fiber reinforced with PMMA and should be prepared as a biomaterial implant to substitute femoral midshaft, the cortical bone. The femoral midshaft, the cortical bone, has an average Young's modulus of 18.6. So this particular implant, femoral midshaft, it has an overall Young's modulus of 18.6 gigapascal. That's question number 9. And the individual Young's modulus are also given. Let's say E1 is the Young's modulus of fiber. It is 197 gigapascal. And E2, which is your PMMA, it is 4.5 gigapascal. Got it? And we are actually making a fiber reinforced PMMA. So if this is a complete tube or whatever you say, shell, this is PMMA, and inside it there are some fibers. These are dot-like structures are your fibers, PMMA and fibers. Now, in order to achieve this overall Young's modulus of 18.6, how much fiber should be added? The volume percent they are asking. Okay, so for that you have to use the mixture rule. So, what is the mixture rule says here? Mixture rule, according to mixture rule, E is equals to E1 V1 plus E2 V2, where V1 is the volume fraction for fiber and V2 is the volume fraction of PMMA. Okay, so what we know that V1 plus V2 should always be equals to 1. And we only have to find the value of V1. We are not concerned about the value of V2 right now. So if we find the value of V1 using this particular expression, V1 plus V2 is equals to 1, we can find the value of V2. So let's rewrite this entire mixture rule expression in terms of V1 only. What we'll get? 1 minus V1. Okay. Now we have all the values except V1. Here V1 is the unknown that we have to find. So put the values of the known things like E we know. E1 is 197 into V1. E2 is 4.5 into 1 minus V1. Simplify it. Okay. So keep all the V1 terms on the one side and the numericals on the other side. So if you do that, what you will get? 10.6 minus 4.5. Here 14.1 you will get the numerical if we bring it this side. By here you will get 192.5 into V1. Okay. So ultimately, what is the value of V1 then? 14.1 divided by 192.5. Okay. So I'm getting 0.01, 0.073, maybe 3. Okay, there is a long decimal, so I'm simplifying it to 0.0733. So this is in decimal form. They have asked in percentage. So if you just multiply with 100, you will get 7.33%. So this value fits within the range. Okay. Is it clear? Moving on. This is the last question and the most controversial one right now. So let's see if we are able to get the answer within the range, because I saw in the board as well, course forum board, there also people are asking what the question number answer for question number 10. Even I got a value which is not within the range. Okay, so let me try this again, solving this question again. Otherwise, I'll discuss this question with Karthik, and whatever the answer, we will let you know through the discussion board. Okay. So here we are asked that we are given that the fiber diameter, dia of fiber, is 10 micrometer. Okay, it is 10 raised to the power minus 6 meter. Now, how many fibers will be required to prepare an implant of 1 centimeter square? Okay, so area of implant. So I'm assuming that this particular geometry is of tubular like, cylindrical like. Okay. So the area of implant, I'm assuming that it is equivalent to the area of a circle. I think in this case it fits very well. So this is pi r square. So we don't know the radius of the entire plant, so no need to write that here. So area of implant is 1 centimeter square. If we convert it to meters, so we have to keep both of them in the same units. So we can do that. We can just convert it. So if we do that, we can keep both of them in meters to be, free from any type of confusion. Like 1 centimeter square is equivalent to 10 to the power minus 4 meters square. So meters square. Or what you could have done, you could have kept your micron unit and converted the centimeters to micron. So we know 1 micrometer is equal to 10 to the power minus 4 centimeter. Okay, so 1 centimeter we want, so we have to, it's simple math, so we can do it. So I'm choosing to go with the meter. So I'll keep all my units as meter in this problem. Okay. Then this is the area of the implant. Now we are asked to how many fibers will be there. So where are the fibers? The fibers are within the bulk, within the volume. So we have to then consider a quantity volume here. We have to bring the quantity volume here. How will we do that? We can do this by introducing a variable length. The volume of implant, we know for a cylinder it is pi r square h. Here h we are replacing with the length. So let's call the variable as L into area of the implant. This is the cross-sectional area basically. This is your volume. So this is the entire volume of the implant. Okay. Just let me quickly check. Yes. Yes.
Are we squaring the 10 power minus 2 to minus 4 in centimeter to meter conversion, ma'am?
Yes, yes. So 1 meter
Okay.
is equals to 100 centimeters. So 1 meter square will be 10 to the power 4 meters centimeter square. So we have to 1 centimeter square will be 10 to the power minus 4 meters square. Okay. And so this is the volume of the implant. Then what will be the volume of one fiber? Again, I'm assuming that the fibers are aligned in the direction, in the horizontal direction, are along the axis, the longest axis, or the rotational axis. If this is the fiber, then this is the axis that is going through. The fibers are aligned along this axis. So the length of the fibers is also same as the length of the entire implant. So the length of the entire implant is L. So length of the fiber is also L. So in that way, we can calculate the volume of one fiber. So it will be L into, again, we know the diameter of the fiber, so pi r square. So here r will be 5 into 10 to the power minus 6. Okay, this will be your volume of one fiber. Now we have to calculate how many of these fibers are there within the implant. So let's call that number n. So the volume of N fibers equals to N into L into pi r square. Okay. So what to do next? We have to find the value of N. For that, we need an expression. So we have to frame an expression. So what is the volume fraction of fibers? Here V1 we calculated, right? This is our V1. We calculate. This is the volume fraction of fibers. We know this value. That is 0.0733. 0.0733. What is this definition? Definition is volume of fibers, total fibers divided by sum of the volume of your implant, total implant. Okay. So we have the volume of total implant. This is the volume total implant. And we have the volume of N fibers. We have to just divide with each other. So it will be N into L into pi into 5 into 10 to the power minus 6 whole square divided by the volume of the total implant. So each are the units are meter cube. So here we have to keep the units constant. Okay. So these gets cancelled. The length L, which was a variable to us, unknown to us, it gets cancelled anyhow due to this ratio. So now we get a very nice expression for N. Just let me bring N to one side so it looks nicer. It is 0.0733. Okay. Divided by pi into 5 square. Pi into 5 square. 5 square is 25 into. Now here again it is squared. So 10 to the power minus 12 and here plus 4. So 10 to the power minus 8. Okay. Now this value will give you the value of N. Now this value should give you the value of N. So if we do it, what we get? So I'm getting around 99.3 to 8.46 around this value I'm getting. So I think that is not the correct answer as per the solution. But let me know if you are also getting a similar value, or if you're also getting, or if you are somehow getting the same answer or within the accepted answer range of this particular question.
When I got around somewhat this value 94267.
Okay. What about others?
I got around the same thing. And in fact, this question, I raised it to the TA Karthik. You're also CC'd in that. What he said was he also worked it out and he also got around the same value. He's going to update the
Okay.
key set.
Okay.
I think
Okay. So,
that mail
okay.
he has not CC'd you in the reply.
Okay, so I was not aware of it. So yeah, then the problem solved for everyone. This is the correct answer. All right, this is the correct answer that we are expecting. So those who are joining today and were not aware of it, you don't worry about it now. The assignment will be reevaluated, and those who will be watching it later and in recording form, for them as well, this is the correct answer. This is the range of the value that you should get, and that will be correct. If you are getting nearer to it, it will be rectified. So that's it. So I hope this session was fruitful to you, those of you all joined. And this is the last time we'll be meeting. And all the best for your exams. I think it's on 23rd, I think. I think it is from 23rd. I don't know the
24th.
exact date.
24th.
24th. Okay, 24th it is there. Okay. So all the best for that. And if you have any additional thing that you want to discuss with me, I would be happy to take it up.
Nothing much. Thank you very much for your time.
Thank you for joining. It has been like a very nice journey actually for these 8 weeks. I also got to learn a lot from this course myself. I was a student just like you, and yeah. Yeah. All right then. If there are no queries, then you may now leave the meeting. All my lecture notes, recordings, they are made available to you anyway. Today's content also you will find. So maybe it will be helpful for you when you will be revising for the or studying for the exam. Okay. Thank you. It was nice interacting with you all, and you guys can leave the meeting.
Yeah.
By when this will be available in the YouTube, the recording?
So it
Or
is
the-
already there. Today's recording.
Yeah, today's recording.
So by tonight you will find it.
Okay, thank you. Thank you.
Yeah. Okay, you guys can leave the meeting if there is no more discussion to be done from your side.